take a 15-minute break. Basically, they will take us away from this place because they need the place to organize for a dinner at 5 o'clock.
Okay. How are you down there? Can you see?
Okay, this presentation kind of follows the work that I presented this morning, and along the lines of studying the effect of bulk phases, particles, and surface oxides, and their roles in propane oxidation and anom oxidation. So this presentation will deal with one specific aspect of this work, in trying to relate rather the changes in just the surface composition of these bulk oxides, not in the underlying mixed metal oxide, with the changes in their ability to selectively oxidize propane. So this is the same table I showed this morning that shows that the optimal catalyst for these reactions consist of vanadium, molybdenum, tellurium, and niobium. And again, oxidation of propane, one of the highest yields observed is close to 60% for research samples, and yields for acrylic acid are lag behind, typically below 50%. And in particular M1 phase that I will show you again in one of the next slides was associated with activity and selectivity of these catalysts in propane oxidation. What I'm going to be talking about today is our recent work in which we employed a model binary molybdenum vanadium catalyst that is essentially totally unselective to acrylic acid as the matrix, as a support that is modified with respect to the surface concentration of mixed metal oxide species and investigated for selective propane oxidation. So again, these are the images from this morning that show the morphology of this catalyst as long needles, and TEM data that suggests that this is a polycrystalline sample. Each rock consists of thin plates, and some of the bricks in these plates are missing, as you recall, which is also evident in the cross-sectional TEM of the same needle, showing these gaps. And again, what's interesting about this oxide as a model system is that in the absence of tellurium and niobium, this system is essentially unselective to acrylic acid and also unselective to acrylonitrile. Okay? So previous studies by other researchers, especially in Japan and a little bit in Europe, in Japan, Wataru Ueda recently investigated propane oxidation, anom oxidation first, on 3 bulk catalysts that contain molybdenum vanadium 3-component and 4-component catalyst. But however, the synthesis conditions that were used to obtain these materials resulted not only in the change in the bulk composition, but also the surface composition of these materials. So in essence, the synthesis conditions resulted in more significant changes in the catalyst than just the surface composition of these materials. And so by contrast with this study, what we decided to investigate is to essentially employ the same basic binary molybdenum vanadium catalyst and just simply modify the surface chemistry by incipient impregnation and look at the result of the effect of these surface promoters present in submonolayer concentrations on the ability of the system to oxidize propane to acrylic acid. So again, what we utilized is the M1 phase that was formed in binary molybdenum vanadium system. We followed a synthesis by Ueda and Rishab Bandari, who was a student that worked on this subject, actually explored a considerable phase diagram in the binary molybdenum vanadium system. So actually his composition was quite different. His bulk composition was quite different from that in Ueda. And then these catalysts, this base catalyst was promoted with various metal oxide species and which allowed us to obtain some insights into their roles. So in this table, what you see is various elements that we used in this incipient impregnation study, as well as the loadings and ICP concentrations of these elements. We applied essentially theoretical modular coverages of these elements that typically correspond to between 7 and 8 metal oxide species per square nanometer of the oxide support. When we actually did ICP analysis, we discovered that because of the very low surface area of these materials, we could not account for perhaps 30 or 40% of the metal oxide we put in the system. So apparently that metal oxide, promoter metal oxide, essentially stayed behind in a vessel that we used for incipient impregnation on the walls of that vessel. So the actual coverages were a fraction of a monolayer. Next, we'll look at the effect of these promoters on the selectivity to acrylic and acetic acid, as well as formation of propene. And what you see here is that the original catalyst shows respectable ability to activate propane into propylene. So you actually see approximately 25% selectivity to propylene. Again, this is done in a following feed that contains 6.3% by volume propane and quite considerable concentration of water vapor in the stream. Water vapor is critical for multi-component catalysts, for these multi-component catalysts to be able to selectively oxidize propane. And also what you see is actually the conversion. These data were obtained at differential conversion, very low conversion levels, typically under 10%. And so what you see is that this catalyst shows about 25% selectivity to propene, but selectivities to acrylic acid and acetic acid are quite low, they're just a few percent. What's interesting is that the addition of just the tellurium by itself in submolecular quantities results in a suppression of selectivity to propylene. However, there is some enhancement of formation of acrylic acid and also acetic acid. Presence of niobium, again, alone in submolecular quantities results in a significant improvement in the selectivity to both propylene and acrylic acid. And when these two elements, tellurium and niobium, are present together on a surface, it results in a quite significant enhancement in these selectivities even further. Okay? Similar result was obtained for the antimony, and in particular antimony niobium doubly promoted catalyst when both of these surface species were present at the surface. However, although you can see that the selectivities to propylene and acrylic acid for the antimony niobium promoted catalyst were a little lower than for tellurium niobium catalyst, this catalyst was much more catalytically active. So in essence, the antimony niobium promoted system appears to be very, very efficient. We looked also at the initial reaction rates for the consumption of propane, formation of propylene, acrylic acid, and acetic acid, and you can see that all of these promoters were essentially promoters of activity, and perhaps antimony was the highest promoter of activity in the system. And you can also see that antimony niobium system was better than tellurium niobium system in terms of promoting consumption of propane and formation of the reaction products as well. The activation energy for propane consumption changed quite a bit, and typically in the range that was reported first previously for similar bulk mixed metal oxides by Ueda, reported activation energies on order of 70 plus minus 5 kilojoule per mole, but they actually span quite a significant range, all the way to 125 kilojoule per mole, which is also similar to activation energies that were previously reported for model supported molybdenum catalysts as well. So these values are still in the range and reasonable. So next we'll look at the surface concentration of the promoter species in these catalysts. And again, we employed low energy ion scattering that I described in some detail this morning. And so what we looked at the essentially the distribution of these promoter species as a function of the distance away from the surface. So quite arbitrarily, essentially we assumed that the atomic layer thickness was equal to the interlayer 001 spacing, which is about 4 angstroms. And we also assumed that quite arbitrarily that at a distance of about 4 nanometers away from the topmost surface, we essentially reach the bulk composition for the promoter elements. And what's interesting, you can see that there is a quite significant difference in the distribution of niobium versus antimony and tellurium for these systems. That niobium essentially is more located at the outmost surface of the system versus antimony and tellurium. And the reasons for that can maybe perhaps understood by looking at the crystal structure of the M1 phase. So what you see here is the crystal structure of M1 phase in the 4-component molybdenum, tellurium, vanadium, niobium composition. For the binary composition, these sites that are occupied by niobium are most likely to be occupied by vanadium. And there's no tellurium in these hexagonal ring channels. So what happens when you put tellurium and antimony as promoters in the systems, they essentially most likely end up going into these channels. That's consistent with the locations of tellurium and antimony as well in the bulk mixed metal oxides with the same M1 phase composition. And perhaps niobium oxide species are just a little bit too large to be accommodated in these channels, and they remain at the topmost surface. Next, we'll look at the distributions of the elements in the binary promoted system, 2-element promoted system, system that was promoted with both niobium and tellurium and niobium and antimony oxides together. And what's interesting is that the extent of enrichment for niobium in these two catalysts is even more significant than it is in the single element case. Perhaps there is some specific interaction that niobium has with some of this tellurium and also the surface of the molybdenum vanadium oxide catalyst that makes it prefer the outmost surface location. And then again, several layers into the bulk. This is where we expect the bulk compositions to be. So clearly, the niobium appears to be concentrated within 1 or 2 surface layers, while tellurium and antimony seem to decline much more gradually into the bulk. So again, the way we obtained the points away from the topmost surface here is by sputtering these surfaces layer by layer with argon ions. And so if one looks at the combination of the low energy ion scattering results and some of the initial insights we obtained by looking at the ability of these systems to activate propane selectively, clearly we are not introducing these tellurium, niobium, and antimony oxides inside the bulk of this catalyst. And so the beneficial effect that we observe primarily associated with the presence of these species at the surface. Therefore, it seems that the creation of these vanadium oxygen promoter and perhaps molybdenum oxygen promoter species in the outmost surface and the topmost surface is relevant in the ability of the system to selectively oxidize propane to acrylic acid. So we clearly see a significant improvement in activity and selectivity of all metal oxide species towards selective activation of propane to acrylic acid. We also see that the pairs of promoters are particularly beneficial, and that kind of correlates quite nicely with the results obtained for the bulk mixed metal oxide system. So that again kind of indicates that really the active sites are associated with just creation of a specific metal oxide bonds in the topmost surface, and therefore perhaps promotion of the system with surface metal oxides represents a promising approach to modify the activity and selectivity of the systems for the selective oxidation and oxidation reactions. So again, I want to flash the slide acknowledging the funding agencies and also group members that helped in the catalyst preparation and characterization work, as well as numerous collaborators on this project. And I'd like to thank you for your attention as well.
Very nice presentation. I wonder if you can comment on the following question. It appears to me that maybe the antimony and tellurium are a sort of scavengers for, let's say, defects. And that's why when they go there first, the niobium doesn't get sucked into those, into those sites, and it's left alone to be more on the surface, in the surface region.
But niobium, you mean for the mixed case?
Yeah, when you add the tellurium, niobium, when you add the antimony with niobium goes up. It means that wherever it was going to go to is occupied by something.
It could be.
And I wonder,
Yeah.
what role that may be part of the synergism.
That's a very good point. Of course, niobium by itself is already enriched in the surface when it's present alone without tellurium or antimony. It's a plausible idea. It's just especially at these levels, it would be pretty tough to characterize what actually happens at the surface. We can quantify the chemistry, but pin these elements to the presence of defects. I'm not sure if there's an easy way to do that. I don't know what you think about that.
It's a tough item.
Yeah.
But I wonder if the antimony and the tellurium really is on the last surface layer. I'll tell you why. Because they cannot terminate in double bonds. Okay? And the surface energy of double bonds is very low compared to hydroxyl. And so it may be that a vanadium or molybdenum, which can terminate, or niobium for that matter, with double bonds, can climb on them. And they're not on the outer surface. The one way to try to nail that is with Raman, dehydration.
That's a nice point.
To see if the antimony, because I've looked at tellurium oxide, I haven't looked much at antimony, but tellurium, but it doesn't make double bonds. Okay.
Well, to comment on that, I would say that's an interesting idea. One way to at least try to go about that is to look at, let's say, even the bulk structure of the one phase that does contain, let's say, tellurium that was published. And we know that in the bulk structure, tellurium essentially is located in this structure.
Kind of on the channels.
It's in the channels, but it's not present as obviously metallic tellurium. So what you see actually behind it is that it has oxygen there behind it. So one would probably so tellurium essentially can be considered as being a low-dimensional component in the system because it forms, I've forgotten which structure it does what. Either in M1 or M2, it's present as essentially as infinite chain of tellurium-oxygen, tellurium bonds. So the question is, are these mu-oxo single bonds? In the other phase, it's actually present as TeO2, I believe, discrete entities. So I think one possibility is to go back to the bulk structure and look at the tellurium-oxygen distance for tellurium in the channels and see if those distances similar to single tellurium-oxygen or maybe even double bond species. I don't know. I don't know what to. That's an interesting point. Yeah.
Maybe along the same line, I was just wondering about the number of defect sites that you have available. And I remember you showed one image where you had cross-section. It was almost like a Swiss cheese look, where you had lots of holes. You pointed it out, those holes, very early on. Yeah, there you go. Is there any way to increase the number of those sites and then increase thereby the number of defects, and then you would have at least a relative way of estimating?
Well, but these are, I think what these are is just missing crystallites, right? That's what I think. I'm not sure if...
so the surface of those is not necessarily what you consider an area where you get absorption, like where you have the layers.
Right, but
So
what...
if you have more of those, then necessarily you would increase the number of defects.
Right, but the question is, what do we define as defects here in the system, right? So
but this would just go along the same lines as how it's
right.
So not necessarily.
Yeah, I hate to interpret what Israel is saying, but it could be, for example, dislocations, right, on a surface, or steps on a surface.
Yeah, but they would just the number of those would,
Yeah.
would exponentially increase as you would have more
Right.
sites.
True.
You could vary those
Yeah.
and measure the catalytic properties. That would be a very interesting experiment.
Right. Well, we haven't thought of that yet. It's an interesting idea.
But in your low energy ion scattering measurement, at each depth, the total element concentration element together is not the constant, right? Is it because
No,
the
it
oxygen
is-
levels different at different depths, or some sort of a wide element together is not the constant?
Well, that's a very good point, actually. That's a very good point. What happens is the topmost surface that I showed is a surface that's been gently oxidized by atomic oxygen to remove surface contamination. When you take these catalysts from the reactor, or just simply expose them to the atmosphere, they're going to have contamination on the surface. When you look at it under ion scattering conditions, perhaps 70% of the surface is invisible because it's covered by carbonaceous deposits, and you cannot really see carbon very well by ion scattering because carbon is so light. So you really need to burn up that contamination, that coke, so to speak, to see the surface. And so when you do that by applying atomic oxygen, you generate a fully oxidized surface, and so you have let's say, a certain state of the surface that corresponds to a certain level of oxygen, surface lattice oxygen. When you spatter away the topmost surface, you spatter away not only obviously metal species, but also oxygen as well. So the subsurface layer will have different oxygen concentration in it. Okay? It will have somewhat different. Okay? But there is really no easy way to quantify that other than spatter away a monolayer, then apply atomic oxygen, and then see what happens to that surface. So it's a little tricky.
So actually, the top layer is not the true top layer.
No, it is. It is
somehow after ion sputtering modification.
It's not sputtering. No, it's not. It's
Or
gentle
gentle,
burning
yeah.
with atomic
Yeah.
oxygen. Okay.
All right.
Unfortunately, there's no other way to do that, and perhaps the only way, there's a slight leap of faith there, and the way to do it, perhaps in this system, is that your surface is not entirely covered by carbonaceous deposits. So there's, depending on the catalyst, 30% to 50% maybe still be vacant. And so you can look at the elemental composition of the surface covered with contamination, and then the composition after it. And perhaps if you don't see big changes, then it may suggest that you don't have preferential contamination of those contaminants at certain specific metal sites. And then you can say, well, my oxygen treatment did not reconstruct the surface to a significant extent. But that's a limitation of this technique. Yeah.
If you follow the logic, the question I asked, is it possible that molybdenum or vanadium or even niobium climb on top of the antimony or tellurium because they on the surface now?
Right.
They have OHs terminating their reactor. Can low-energy ion scattering really discriminate between antimony, tellurium being in the same outermost surface layer, the terminating layer, or vanadium's partially, linked to one of the hydroxyls in sort of an angle? Can you discriminate between those situations?
Well, I mean, it's a line of sight technique, okay, and so if niobium is essentially on top of antimony, then you will not see antimony.
Yeah, it could be on the just bonding to one, like antimony oxygen niobium bond or something. Tellurium oxygen niobium bond in the same plane.
Then you'll see both. If
Yeah.
they're in the same plane, you will see both. But you clearly, what you also clearly see is, I think with very little doubt, is that tellurium and antimony concentrations seem to decline much more gradually with distance to the same value. So It
Your
appears-
first, your outer layer and your so-called one monolayer down, the 2 monolayer down, the 3 monolayers down, within experimental error does not change.
Right. And so when you look at this kind of system here, which has 2 promoters at the same time, it could be that tellurium does penetrate several layers into these channels, and then maybe niobium is associated, sits on top of that tellurium. So tellurium here may prevent niobium from going anywhere significantly, but it's just it's tough to say.
I think we do model systems. Okay.
Well, this is a model system too. It's a binary M1 orthorhombic phase. So, and it has these channels that are unique.
Thank you.
Thank you.
I think Vadim